Every second, you are processing an avalanche of data. Your system is decoding millions of pixels of light, calculating physical balance, regulating heart rate, and synthesizing language all at once. A modern supercomputer would struggle to handle this simultaneous, real-time data stream without crashing. This creates a biological paradox. The brain manages this workload using 12 to 25 watts, the energy draw of a single LED bulb. Under traditional computing logic, this should cause immediate system failure. The power supply is too small for the incoming sensory data. The brain survives this energy constraint through a masterclass in computational delegation, dividing labor across specialized biological hardware to prevent system overload. Mapping the brain's architecture reveals a modular network of subprocessors, beginning with the deepest layers connected to the spine. This central column is the brainstem. It acts as an autonomic background processor, managing functions requiring no conscious effort. It handles the critical maintenance tasks of the body, maintaining heart rate, regulating breathing, and managing digestion, without the system ever alerting the conscious mind. Shifting focus to the lower rear of the brain, we find a dedicated physics engine called the cerebellum. This specialized region regulates fine motor movements and constantly calculates the complex, real-time physics required for human balance. Without a dedicated localized processor for these physics calculations, upright human mobility and navigation would be entirely impossible. By offloading repetitive autonomic functions and balance calculations to these lower processors, the brain prevents its primary CPU from overloading. Moving up the architecture, we reach the regions responsible for threat assessment and complex logic. Deep in the center of the brain sits the amygdala, an almond-shaped cluster that functions as the system's high-stakes survival drive. It processes raw emotions, triggers survival instincts, and categorizes events for long-term memory storage. This modular efficiency supports the largest component of the biological supercomputer, the cerebrum. The cerebrum takes up a staggering 85% of the entire brain's volume. As the system's main CPU, the cerebrum controls voluntary muscles and executes high-level operations, like complex thought, feeling, and learning. Allocating this much processing power to sheer intellect is only possible because the smaller coprocessors manage the immediate burdens of staying alive. This hardware is highly sensitive and chemically influenced, meaning its processing efficiency can be altered by the user's physical state. When we are mentally fatigued or stuck on a difficult problem, the cerebrum often struggles to absorb new information. Engaging in a period of physical exercise triggers the production of a specific chemical that travels through the system and alters the brain's internal state. This chemical release makes the brain significantly more receptive, increasing its ability to process and learn difficult new concepts. Stepping away from a frustrating problem to engage the physical body is more effective than forcing continued mental strain, as it resets the system's capacity for learning. The efficiency of this biological supercomputer is tied directly to your movement. Optimizing your mental performance requires